Okay, so here's a Zoom meeting for Physics 231C. This week we're studying chapters 5 and 6. So chapter 5, there was a Zoom meeting about chapter 5 a week ago. Chapter 6 is on momentum and collisions. The long homework assignments for chapter 5 and chapter 6 are both due on Monday. Most people have done at least a good portion of chapter 5. Chapter 6 is a bit shorter. Chapter 5 is on energy, and that's a very important subject that we'll be using throughout the rest of the semester. So you really have to know how to understand it, energy now. Now, in chapter 6, we introduce another concept called momentum. It's used in describing collisions and other ways. It has another conservation law. Like energy has the conservation of energy, very important conservation law. And momentum has conservation of momentum. And that'll be important in describing collisions and other things. So you have to read the chapter and take notes. So for example, here's some of the notes you should have. And most of the notes are going to be equations, maybe a few pictures and so on, but most of the notes will be equations. And these are some of the notes or equations you should have written in your notebook. First of all, what is momentum? Momentum is just a quantity which is used in describing motion, but it goes beyond just kinematics. It's defined as the mass times velocity of a moving object. So any moving object has momentum equal to mass times velocity. Now, of course, velocity is a vector, so that means momentum is also a vector. So it has a direction. The direction is the same as the direction of the velocity. We use the letter P to stand for momentum. Another concept which is introduced in the chapter is impulse. Impulse is defined as force times time, where F is the force acting on an object, delta T is the time during which the force is acting, and this is assuming that the force is constant over that time interval. So the definition of impulse is force times time. Now, it turns out, because of Newton's second law, that quantity, force times time, is equal to the change in momentum that occurs over that time interval delta T. There's a conservation law, and we can use the concept of conservation of momentum to solve various physics problems. Conservation of momentum says, and it's really a consequence of this equation and Newton's third law of motion, says that the total momentum of a system of moving objects is constant. So if you have some system, let's say with several particles in it, and they're moving around, the sum of all the momenta at some initial time will have to be the same as the sum of the final momenta at some later time. So the momentum of the particles are all changing. You know, each particle is going to be changing in position and momentum and velocity. So each particle will have a momentum that may be changing, but the sum of all the momenta will not be changing. It will be the constant. It'll be the same for the initial state and for the final state. And that gives you some important information about how things are changing in this system. And that equation will tell you some things about the system. A very good example of this is a collision. A collision, you have two particles which bump into each other. Before the collision, they have some momenta. After the collision, they'll have different momenta because the force that they exert on each other when they collide will change their direction of motion, their speed, and so on. But what will not change is the total momentum of the system. So that's called conservation of momentum. And we'll see some examples of that in a minute. Now, there's a couple of sections on collisions. The two simplest kinds of collisions are elastic collisions and inelastic collisions. In elastic collisions, energy is conserved. That is to say, kinetic energy of the colliding objects will be the same before and after the collision. In inelastic collisions, the kinetic energy is not conserved. So elastic objects like rubber objects or steel objects colliding will have pretty much elastic collisions. But if you have a collision between something which is not elastic, not made of rubber, not made of steel, something made of something which like clay, something that can be distorted or so on, those will be inelastic collisions. And in inelastic collisions, energy is not conserved. Of course, total energy is conserved, but when I say energy is not conserved, I mean the kinetic energy is not conserved. If a car runs into a truck, the car will be all crumpled up. There's some energy which goes into crumpling up the car. So some of the initial kinetic energy will be converted into the energy needed to to distort the shape of the car. So that would be an example of an inelastic collision. Perfectly inelastic collision is one where two objects collide and stick together. That's called perfectly inelastic. So anyway, you should be reading it in chapter 6 and taking notes about these different ideas and equations. So let's go over a couple of problems to see how these concepts and equations are used. So here's a problem from the assignment, which is due Monday. It's about the collision of atomic nuclei. But we don't really need to know anything about nuclear physics or nuclear reactions. All we need to know about is conservation of momentum. So it says, Canada's CANDO nuclear reactors use heavy water to slow neutrons. The neutron, which has a mass 1.67 times 10 to the minus 27 kilograms, collides with a deuterium nucleus, which has a mass of about twice that, 3.34 times 10 to the minus 27 kilograms. And because of the collision, they'll slow down. It'll be an elastic collision. So it says here, consider a head-on elastic collision with initial neutron speed V0, and initially the deuteron is at rest. Deuteron is a hydrogen isotope. Then part A, find the neutron speed after the collision in terms of its initial speed, V0. And then there's a part B, how many such collisions must occur to reduce the neutron kinetic energy from 1 MeV, the kind of energy it might have when it's produced in a nuclear reactor, to 1 electron volt. which is the energy, it'll be reduced to that energy. We're talking about kinetic energy here, after some number of collisions. So that's the problem. It's really to analyze an elastic collision between two particles with mass m1 and m2. And it doesn't give a value for the neutron speed. So we just want to know what's the final speed after the collision. That will be something proportional to the initial speed. We just need to calculate that constant of proportionality. So we always do these problems in the same way. We start by drawing a picture. So here's a picture. We're going to have a collision. It's going to be a head-on elastic collision. So here's a picture before the collision. You have the neutron coming in with a speed v0, and you have the deuteron, the doubly hydrogen isotope. Here's the picture after the collision. It's an elastic collision, so the two particles will bounce off each other. There'll be a force, there'll be equal but opposite forces on the two particles by Newton's third law. The force on the neutron will cause it to bounce backwards. The force on the deuteron will cause it to bounce forwards. Why does the neutron bounce backwards? Because it's less massive. Its mass is only half as much as the deuteron. So you can sort of picture this in your mind's eye. A small object hitting a heavier object is going to bounce back. And let's say the speeds are v1 and v2. If it's a head-on collision, they'll be in the same line. So the first step is to draw a picture. Here's actually two pictures. We need two pictures for this problem. The next step is write down equations. And we have the equations for an elastic collision, which is that the total kinetic energy is constant and the total momentum is constant. Now, those aren't the equations that I've written down here. The equations that are written down are from the textbook, taken from the textbook. In the textbook, there's a section on elastic collisions, and they'll solve this general problem: an elastic collision between a moving object and an object at rest. And the speeds after the collision will be proportional to the initial speed. And the constants of proportionality will depend on the masses, or actually ratios of masses. So the particle that was moving initially, that's the neutron, v1, will have an outgoing speed m1 minus m2 over m1 plus m2, v0. How do I know? Well, that's the solution of the problem of elastic collisions in the book. This corresponds to an elastic collision in one dimension. And you can find that in the section on elastic collisions. And what about the heavier object? What's its speed after the collision? It'll be 2m1 over m1 plus m2 v0. So, reading the section on elastic collisions, you'll find these two equations. Write those down in your notebook. You'll need to use those equations whenever you have a problem with an elastic collision. All right, so let's think about this. M1 is the neutron, M2 is the deuteron. So M1 or M2 is 2 times M1. So this will be like 1 minus 2 over 1 plus 2. 1 minus 2 is minus 1, 1 plus 2 is 3. So V1 will be minus 1/3 V0. So it'll bounce off going backward at a speed 1/3 of the speed it had before the collision, but going backwards. Now, what about this equation? M1 is 1, M2 is 2, so this is 2 over 3 V0. So the heavier object will bounce forward. It'll be knocked forward, and its final speed will be 2/3 of V0. I'm not sure exactly how you're supposed to present the answer here in the box, but anyway, looks like V0 is not given. Okay, so maybe you just have to write down it's in terms of V0, the neutron speed will be 2/3. Minus 1/3. Now that's the velocity. The speed will be plus 1/3. Velocity negative just means it's moving backwards. Now, that neutron will hit other deuterium atoms. Each time it hits a deuterium atom, it loses some speed. And so part B says, how many collisions must occur to reduce the kinetic energy from 1 MeV to 1 electron volt? Well, the change in kinetic energy, remember, kinetic energy goes like V squared. So if the change in the speed is 1/3, the change in the kinetic energy is 1/9. It's not 4/9. Yeah, this is a mistake. Not 4/9, but 1/9. Each time it undergoes a collision, its kinetic energy is reduced by 1/9 because the speed is reduced by 1/3. And kinetic energy goes like square of the speed. If you have n collisions, then you would have 1/9 to the power 9 would be the change in kinetic energy from when it first started. And you want to change that from 1 mega electron volt to 1 electron volt. So the change in the kinetic energy should be reduced by 1 over 10 to the 6, 1 over a million. And the unknown in part B is what's n? How many collisions does it take to reduce the energy, kinetic energy, by 1 million? All right, so that's an example of a problem where we're really using the fact that energy and momentum are conserved. We didn't actually write down those equations because we found the relevant equations for the elastic collision in the chapter. So you should have those written down in your notebook. Or here's another example. Two simple pendula hang side by side. One is lighter, one is heavier. So let's call the lighter one mass little m and the heavier one mass capital M. The lighter bulb is pulled aside until its string is horizontal. So the lighter one is pulled aside. So this is the initial condition. The string is horizontal. The heavier pendulum is just hanging straight down. Now release this mass little m from rest. What will happen? Well, the pendulum will swing down and hit the bob of the other pendulum. So there'll be a collision. So it swings down and collides elastically with the other bob at the bottom of the arc. It's moving on a circular arc because the length of the string is constant. So it'll swing down like this. and then collide with the heavier bob. Now the question asks for the height for each of the two bobs. But to analyze this, we have to understand the collision. When these two spheres collide, one will move off to the left, that's the heavier one. The other one, which is lighter, is going to move back to the right if it's an elastic collision. So we start by drawing a picture. Well, here's a picture. Here's another picture. We're going to need another picture. So let's draw another picture. This is the picture where we have pulled little m up to where its string is horizontal. This is another picture where little m has swung down a little ways to where its angle is theta. Now we're going to need another picture. So here's another picture where the two are colliding at the bottom. And we always label the picture with the relevant variables, not numbers, just variables. Here, the relevant variable is the speed of little m and the speed of capital M. This would be just after the collision. Just before the collision, little m has a certain speed. Capital M is at rest. Just after the collision, their speeds are v1 and v2. So we have various things to figure out, but we've got a picture of everything. We can use conservation of energy for this part of the problem, where m is swinging down. So if you think back to chapter 5, conservation of energy says that the total energy of this pendulum is constant. Now, what is the energy? Well, there's kinetic energy, a half mv squared, and there's potential energy. The potential energy of mass in gravity is mgy, where y is the height. So you see here, if we call this y equals 0, if we call, well, let's see. If we call this height 0, then here the height is L. It's one radius of this circle above ground level, which is 0. So it's mgy, where y is equal to L. Now, by a little bit of trigonometry, you can see here that y, the height above ground level, is L times 1 minus the cosine of this angle. L is this distance. This distance is L times the cosine of the theta of the angle, just by looking at this as a right triangle and using trigonometry. So the height above ground level is L times 1 minus cosine theta. For any point on the downward trajectory of little m, the total energy will be 1/2 mv squared plus mgy, and y is L times 1 minus cosine theta. So that's constant. So in particular, that's equal to 1/2 m, no, that's equal to mgl. So this constant, try it this way. So this constant is mgl, because that's the value that it has when it's up at the top. V is 0 there. The height is L. This height is L. So this corresponds to theta equals 90 degrees. At theta equals 90 degrees, the cosine is 0. So this constant is equal to mgl. And it's also equal to 1/2 mv1 squared. Now I know L, I know M, I know M1, I know M2. The only, so actually this should be M1. This should be M1. The only uncertainty, the only unknown here is V1. So I can calculate this and calculate V1. Now I have a collision just like the collision I saw in the other problem. One particle at rest, that's capital M, one particle with a given given velocity, in this case V1, and now I have an elastic collision. Actually, I better not call this V1. I better call this V1, V0. That's the velocity just before the collision. So as it's swinging down, just before it collides, it has a velocity given by 1/2 mv0 squared is equal to mgl by conservation of energy. So now I know V0. Now I can use those same equations that I used in the previous problem that come from the analysis of an elastic collision in one dimension. So V1, that's the recoil of the lighter bob, is M1 minus M2 over M1 plus M2, V0. V2 is this speed where it's bounced forward, 2M1 over M1 plus M2, V0. So where did these equations come from? Out of the book, but I wrote them down in my notebook when I was reading the chapter, so I have those. Now that's not what I want. What I want is, how high will the two masses go? Well, now I can go back to conservation of energy. Take this as the initial state. This has a velocity V1. That means the mass will swing up to a height Y1. 1/2 mv1 squared will be mgy1. And as for the heavier mass, it has a speed V2. It'll swing up to a height Y2, where energy is conserved. 1/2 mv2 squared is mgy2. So I've solved for the unknowns, Y1 and Y2. And that's what goes in here. Calculate the height that each bob will reach. This will be Y1. This will be Y2. So you see, draw the picture and label it. You use the equations, and you can see what the equation should be from general equations and from the labels on the picture. And then you apply a little bit of algebra. Now you pick up your calculator. So now in order to calculate Y1 and Y2, Y1 will be a number with unit of meters. I have to know L, M1, and M2, and G. So now at the very end is when I need my calculator. Any questions? Where does momentum come in here? Well, I never mentioned momentum, but this is a collision. So to analyze a collision, you have to use conservation of momentum. It's the analysis of conservation of energy, which leads to these two equations. I didn't derive them here. I just took them out of the book. But that's calculated in the book, which applies to any one-dimensional collision, elastic collision. The last problem for today is another collision problem, another elastic collision problem. a little more difficult than the others. The mass of a basketball is 0.624 kilograms. The mass of a tennis ball is 0.058 kilograms. Now, drop the two balls together like this, with the basketball underneath, the tennis ball on top of the basketball. Now, hold them there so that they're both in that position, and then let go simultaneously so that they both fall together. Another quantity I need is the radius of the basketball, or the diameter. What's the diameter of a basketball? I don't know. It's written down here as 24.2 centimeters. That's the diameter. Maybe I looked that up on Google or something. I mean, all basketballs are supposed to be standardized. So I could just look up on Google, what's the diameter of a basketball? 24.2 centimeters, 0.242 meters. Let's say I hold them up at 1.5 meters. That's about head height, or it depends on how tall you are, but that's sort of around shoulder height. So you hold them up around shoulder height, let's say Y0, and then you let them go. So what's going to happen? Well, the basketball will hit the ground and bounce back up. That's an elastic collision. Think of balls as being elastic. The tennis ball will fall down at the same time that the basketball is bouncing up. The tennis ball will be coming down, and so there'll be a collision between the basketball and the tennis ball. And that's going to bounce the tennis ball quite high. So the question in the problem is, how high will the tennis ball go? And the answer is quite high. So let's see how to calculate that. We start by drawing a picture. We already have a picture, but this is maybe not a very good picture. We need a better picture, so let's draw our own picture. We have the picture just before the tennis ball collides with the basketball. You know, in the instant that the basketball has bounced off the ground and collides with the tennis ball, which at the same time is moving downward, there's a collision. And so here's a picture of the collision. There's the basketball, it's right at ground level. Here's the tennis ball, it's right at the diameter of the basketball. The basketball has a velocity V1. That'll just be the velocity of the ball when it falls down that distance. So I can use conservation of energy to figure out the velocity of the basketball. The velocity of basketball will be 2g y0 minus r by conservation of energy. So that's V1. V2 will be the same, only moving downward. So that will have a velocity minus 2g times y0 minus r square root. 1/2 mv2 squared is mgy. The change in y is not y0. It is y0 minus r. It's fallen down to the point where it's in contact with the basketball. So the basketball is a distance r from the ground. The tennis ball is a distance r from the center of the basketball. And so the height of the tennis ball will be y0, its initial height. That initial height would actually be the initial height of the tennis ball. Well, I don't know if these equations are exactly right, but anyway, you know the initial height of both balls. And what goes in here is the change in the height. So really it should be the square root of 2g delta y. And there'll be a delta y for the tennis ball, and there'll be a delta y for the basketball. And so the delta y is a little different for the two. So do this carefully. I'm not sure I've got these exactly right. Now there's a collision. And so now you write down the equations for a collision. This is not the same as the collisions we considered in the previous two problems, because in the previous two problems, one object was moving and the other object was at rest. Well, in this problem, they're both moving. So you have to go back to the fundamental equations. The fundamental equations are conservation of momentum. So mv1 plus little m v2 is equal to m v1 prime plus little m v2 prime. So v1 and v2 are the velocities just before the collision. v1 will be positive, v2 will be negative. v1 prime and v2 prime will be the velocities just after the collision. So this is the total momentum just before the collision is equal to total momentum just after the collision. And similarly, the total kinetic energy just before the collision here compared to the kinetic energy just after the collision, 1/2 mv1 prime squared plus 1/2 mv2 prime squared. So v1 and v2 are these velocities, which I know from the fact that I dropped this a distance of 1.5 meters. v1 prime, v2 prime, I don't know. So here are the equations for v1 and v2. Well, v1 prime and v2 prime, I don't know. And I can't solve either one of these equations. I have to solve them simultaneously. So here I have an algebra problem, solving two equations with two unknowns. So, you have to solve two equations for two unknowns. You know how to do that. You just solve this equation for, let's say, v1 prime, put that in here, you'll then have a quadratic equation for v2 prime. And so everything is known here except for v2 prime once I substitute v1 prime in here, because v1 prime is known in terms of v1, v2, and v2 prime. So now I have a single equation for one unknown, let's say v2 prime. That will be the final velocity of the tennis ball. That is to say, the velocity of the tennis ball just after the collision. So that gives me so after a bit of algebra, that gives me the speed of the ball, tennis ball, moving upward from a height of, I guess it's 2r. Now, how high will the tennis ball go? Well, let's say it going to go up a distance h, capital H, will be the final height of the tennis ball. Now I can use conservation of energy again. I use conservation of momentum and energy for the collision. Now, once they've collided, I just use conservation of energy for the tennis ball. Its final energy will be mgh. Its initial energy, that is to say, just after the collision, will be 1/2 mv2 prime squared plus mg2r. So it's here at a height of 2r with a speed of v2 prime. I calculated v2 prime by solving these equations. I can plug that in here. The only unknown here is h. So now I can calculate h. Just divide both sides of the equation by mg. So you see how it goes. We draw a picture with labels on it. We write equations. We analyze the equations. we could analyze these equations to calculate V2 prime. Not quite done yet. We have one more equation where we know V2 prime. Now we analyze this equation to calculate H, and that's what goes in here. How high will the tennis ball go? H. And the answer will be surprisingly high. You know, I dropped it from a height of 1.5 meters, about shoulder height. It's going to go way over my head. And that's the problem. Any questions about this or anything else? Here's a question. For the first problem you went over, should N be the answer for part B? Yeah, N is the number of collisions. Let's see. How many collisions must occur to reduce the energy from 1 MeV to 1 electron volt? So you're trying to reduce the energy by 1 over a million. And on each collision, the neutron speed decreases from V0 to, what I say, 1/3 or minus 1/3 V0. So the kinetic energy changes by 1 over 9. So on each collision, there's a reduction in kinetic energy by 1 over 9. So on the first collision, it's 1 over 9. On the second collision, it's again 1 over 9. Third collision, it's again 1 over 9. So it's 1 over 9 times the number of, to the power of the number of collisions. It's 1/9 times 1/9 times 1/9 times 1/9 for the number of collisions. And that total change has to be 1 over a million. So the unknown is N. And that's what the question is asking for here. Can you explain 686? Well, I don't have it here, but if I look it up, let's see, I don't have it here. I would have to look it up on ln kappa. I might be able to say something about that. If I go to ln kappa, that's chapter 5. Here's chapter 6. No, 686, this one. 686. Oh, unfortunately, the problem's in the book. Oh boy, the problem's in the book and I don't have the book with me. So there's a scattering angle. Oh, it's helium scattering from gold. Okay, so it's helium scattering from gold. There's a question. There's an answer to the question. So here's a question from a student asking for hints. Here's an answer from Dr. Mussolf giving some hints. I think what this is, see if I can draw on this. Let's see, how do I draw on this? I think you have a problem like this. You have a particle, which is called alpha. That's an alpha particle. It's hitting a gold nucleus. So this is the gold nucleus. This particle will be repelled from the gold nucleus, and it will scatter off in some direction. And this is probably the angle, the scattering angle. And meanwhile, since the alpha is hitting the gold nucleus will be repelled, will be bounced forward somewhat. So this will have some scattering angle. So that's given. So that's 25. Let's see what happened to my. So this is going to be 25. Degrees. This will have a certain mass, which will be small m. This will have a much bigger mass, call that capital M. This has a certain speed, v0. This has a different speed, v1. This has a different speed, v2. Now, these are actually velocity vectors. So v2 and v1. So you have to remember that velocity is a speed. So you'll have an x component of velocity, which is in the direction of the initial particle, and a y velocity. All right, so now you want the two velocities. So you want the HE velocity and the AU velocity. I'm not sure what else is given in the problem, but the answer is how do you solve this problem? Well, it's conservation of momentum. You have an equation m v0. That's the initial momentum, and that's in the x direction. So that's m v1, nope, m v1 cosine theta. That's the x component of the momentum of this alpha particle, and then plus m v2 cosine of the other angle. Cosine of the other angle, let's call the other angle phi. We don't know what phi is. So this angle will be phi. So that's the x component of momentum conserved. And the y component of momentum is conserved. So 0, it has no y component before the collision. It's just moving in the x direction. Well, that will be m v1 sine theta. And then this one will be moving in the other direction. So that'll be minus m v2 sine of phi. And you also have conservation of kinetic energy. So you'll have a third equation, which says 1/2 mv0 squared is 1/2 mv1 squared plus 1/2 capital mv2 squared. So we have also the equation for conservation of kinetic energy. So you have three equations. You have several knowns and several unknowns. Theta is known, it's given, 25 degrees. Phi is not known. So you're going to have to solve for phi. The masses are known. V1 and V2 are not known. So I guess there are three unknowns. V1, V0 is known. That should be given. V1 and V2 are not known, and phi is not known. So you have three unknowns and three equations. So it's back to algebra. You have to solve three equations for three unknowns, and you can't solve any of the equations by itself. You have to solve all three of the equations simultaneously. I'm pretty sure there's a hint about this on the hints page. So to make sure that you're getting the right equations, look on the hints page. For this problem. The hints are not posted. The hints are not posted? Are you sure? They should be posted. Let me check if the hints are posted. Let's see, how do I do this? Let's see, we go to the supplemental content. Okay, then I'll have to go and post the hints if they're not posted yet. I go to supplemental content, hints folder, hints for problem sets. Let's see. That's problem set 4B. Yeah, here it is. 686. That's 686. So come down here. I've got to get rid of this. $675. Yeah, okay, unfortunately, I've got all this junk that shows up. I don't know how to get rid of that. But here is problem 686. Here is the picture. Okay, so it's got the picture. It doesn't have any more than just the picture. I see. So hints are not given for problem 686. The hints are posted, but there's no hint given for problem 686. But you just use a conservation of momentum and energy, kinetic energy. And that'll give you three equations with three unknowns. Now, if you can't see the hints, then you need to log out of ln kappa and log back in. Because sometimes ln kappa will be using an old login. And the old login may not have had the hints, but the hints are there now. So you need to log out of ln kappa and log back in. This folder. Wait a minute, now I am confused. Here's hints for problem set 4A. Well, now that's the hints for problem set 4A, but a minute ago I was getting the hints for problem set 4B. All right, well, I'll have to wait until I go home, but I'll go home and make sure that the hints are working for both 4A and 4B. And maybe I'll add something because when I was looking at 4B, I wasn't seeing anything except the picture. So maybe I'll make sure that these equations are written down so that you'll have also the equations to start from. But I'll have to wait until I get home to do that. You can see 4A, but not 4B. Okay, that's weird. Okay, well, I'll go fix those. All right, so we've taken about an hour. Any last questions? Then guess I'll stop the recording. Not what I want. Let's see. Okay, I'm going to end the recording.